Now we're going to talk about the geometry, the one that has a lone pair on a non-central. And of course, the lone pair is electron. An electron has repulsion with another electron, right? So in a Vesper theory or valence shell electron pair repulsion theory, the geometry will be the one that has the least electron repulsion. Okay. All right. Let's take a look at the effect of the lone pair. So for ozone, the Lewis structure, it looks like a linear, see that? But you have to consider the lone pair as well. So I want you to think about the lone pair as the big, fat, crying baby that no one's want to be around, right? So this one need a lot of space, right? Even much more than a non-central atom. This lone pair need much more space, right? So the lone pair right here on the central atom of ozone will push the other bond away, right? So look something like this, right? And it's not a linear anymore. We call it bent. It's bent from the linear. Okay. Now from the look at the structure of ammonia down here, NH3. All right. 3 non-central. It's supposed to be trigonal planar. And that's supposed to be trigonal planar. All hydrogen are on the same plane. So I'm going to twist this structure a little. So on the same plane. So okay, so on the horizontal. Now, but nitrogen have one lone pair. This lone pair will push everything else the other way. In this case, push everything else downward. All right. So you will get up to got to that geometry. In this one, it's not trigonal planar anymore because all hydrogen atoms are not on the same plane. In this case, we call this structure a trigonal pyramidal. Looks like a pyramid. You know? All right. So in this case, you should be able to predict a bond angle, roughly bond angle. So, all right, from 3 non-central. All right. So I'm going to replace. Let's say if I replace. Let's start right here. So 3 non-central. The bond angle is 120 degrees. Okay. I'm going to replace 1 non-central with a lone pair. All right. So the lone pair again. So needs a lot of space. We'll push these two non-central even more downward. Yeah, we call it bent. The bond angle going to be less than 120 degrees because this guy need much more, a bit more space than the non-central atom. Okay. All right, let's try right here. So let's say I replace, so go to tetrahedral 109.5. All right. Replace 1 non-central with a lone pair. So lone pair will push everything else downward. Right. We got trigonal pyramidal. The bond angle right here is going to be less than 109.5. If I, from trigonal pyramidal, if I replace one non-central with another lone pair, also right here on the left side, right here, these 2 lone pair need even more space than a 1 lone pair, right? I'm going to move this thing right there. Look like bent, but this 2 lone pair will push these 2 non-central even more. The bond angle going to be even less than 109.5. Okay, give you some examples. So methane, CH versus CH4, the bond angle is 109.5. When it got 1 lone pair, the bond angle goes down to 107.3. All right. When you got water, so we got 2 lone pairs, the bond angle go down to 104.5. Right? You don't have to memorize this bond. Only one bond that I asked you to memorize is 109.5. The rest you can predict. You can predict all going to be less than 109.5, going to be even less than 109.5, and that's all you need to do. I'm not going to ask you like what is the exact bond angle. No, like no way. Okay, no one knows. We have to do experiment, like measure it. Okay. All right. So we have class activity number 4. Okay. So you have to predict the molecular geometry of each of these compounds. Okay. All right.